Hi, and welcome to Lecture 25. This lecture may be kind of an important one, and it may be one that you return to a couple of times. This is the first time that we're going to be looking at kind of the second half of calculus, which is called integral calculus. To get at it, we're going to approach it in a slightly different way than the way the textbook approaches it, and I really want to do this for a reason. Namely because the idea that we explore in integral calculus, or when you're studying integration, is an idea that is not really at all connected directly to derivatives or differential calculus. And, that's not quite true. It is connected, but it's not connected as strongly as most people think that it is. So what I want people to develop is a very good idea of what an integral is. And unfortunately, the idea of an integral is sort of difficult. So I'm going to tell you what an integral is in very general terms right now, and then we're going to be studying in this particular video a lot of ways that we use to talk about integrals, and then eventually we'll develop things that people know and how to calculate integrals. So there's two aspects to integrals or integration. One is recognizing an integral when it occurs, kind of naturally, whether it's in an application, in nature, in a modeling type of situation, recognizing an integral. And then the second problem is how to calculate it. And it turns out that both of those are kind of difficult. And for those of you who have had calculus before, I need to tell you to please forget anything you've ever learned about integrals, because probably the only thing that you remember about integrals is that you use this idea of finding an antiderivative and plugging in two numbers and subtracting, and that's your answer. And it turns out that that does work sometimes, a lot of the times, but it doesn't really tell you anything about what an integral is. It tells you how to compute it sometimes. So I would like you to get that out of your head. We'll come back to that idea in later classes, but not right away. Right now I want to tell you exactly, well, not exactly, but I want to tell you in general terms what an integral is. So here it is. An integral, my favorite type of question, what kind of thing is it? An integral is a limit. But it's a limit that's kind of different from any that we've talked about so far this semester. This is a limit of sums, or actually, it's a limit, I should say a limit of a sum of products. This is getting complicated. It's a limit of a sum of products of things. Things. Yeah, don't you love that one? What are these things that we are multiplying together and then adding up? Well, the things are things that look like this, obviously. They are two things. You could say thing A and thing B, and they're being multiplied together. And I can't tell you anything about the first thing, but the second thing is always some kind of a delta x. So, what is an integral? It is a limit of a sum of products that you obtain by multiplying things together, one of which could be just about anything, and the second of which is always a delta x. All right, so you can sort of file this away somewhere, and it'll be made much more precise as you go along, and nobody's going to be happy about making it more precise than that. But I'll try to explain where this comes up in the next few minutes, and we'll look at a couple of sort of sample problems. So this is getting us really into chapter 5 of the textbook, the first couple of sections. We'll come back and do the last section of chapter 4 a little bit later. So in chapter 5 at the beginning, the first section, which is where we really are going to be in terms of the problems that you're going to be working in class on Friday, but in terms of this integral, they don't tell you this integral yet, but that is what we're doing. And the example that they bring up is the idea of finding the area. Finding the area of some kind of a region. And area is going to be looked at in kind of general terms. So what I mean by that is, many of you have heard this phrase, I want to know what the area under the curve is, but that's not exactly what we're going to be doing. Here's a function, for example, right? And I didn't mean it to look so regular. It's maybe sort of like that. And it's not intended to be a sine or a cosine or anything periodic, but the area would correspond to the area that's between the function and the x-axis, except that I want to consider that area as being maybe positive or negative, which doesn't make any sense in the real world, but this part of it would be positive area and this part of it would be negative area. Now, how do we really do that? Well, that's what this sum of products of things is going to be like. So here's how it works. We're going to take a general function like this. Let me draw it again just so that it doesn't matter what it really looks like, and it doesn't matter whether it goes above or below the x-axis. But we're going to take that function and we're going to think about it on an interval from a to b. And outside of that interval, I really couldn't care less what's going on. But on the interval from a to b, I'm going to think about the problem of calculating this kind of area that can be positive or negative. You might think of it as a mass or a weighted mass. How much weight is there above here versus below here and above here and below here? The way this picture looks, it looks to me like there's more above the x-axis than there is below the x-axis. So if this were kind of a battle, the positive numbers would win. There's more mass above the x-axis than there is below the x-axis. At least that's the way it looks to me. And the integral would pick up on that. It would sum up, in some sense, positive numbers here, negative numbers here, corresponding to the area, and then positive here, negative here. And in the end, it would give you a number that corresponds to the total area, considering positive and negative. So how it's going to work is we take the interval that we're interested in and start by chopping it into any number of pieces. Make it regular. It doesn't have to be. It turns out you can chop it any way you like. But I'm going to assume, at first at least, that we're going to chop this interval into n pieces or n subintervals. And all of the subintervals are going to be the same length. All right? And how big are they? Well, that's the delta x that I was just talking about. So every subinterval, this one, even this one, although it doesn't look like it, they're all intended to be delta x long. Now we're going to have a lab on this next week, but I will jump the gun a little bit and tell you how to calculate this all. If we have set n subintervals, and if the length of the whole interval if the whole interval goes from a to b, then the whole length from here to here is always the bigger number minus the smaller number. So b minus a is the length of that whole interval. And if I'm dividing it into n subintervals, then each subinterval is that big, b minus a over n, right? The whole length divided by however many of them I've got. So for example, if a is 0 and b is 10, then the whole interval is 10 units long. And if I'm dividing it into 50 subintervals, then it would be 10 divided by 50, and each one would be 1/5 of a unit long. Here I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Looks like 11 subintervals, and this thing looks like it's about 9 inches long. So it'd be 9 inches divided by 11. So whatever that turns out to be, 9/11ths of an inch per subinterval. And this, of course, is delta x. Okay? So each subinterval is that big. And what we're going to do on each subinterval is calculate a y value. Now, how do we do that? It turns out there's infinitely many ways, and it doesn't really matter but we try to be consistent about it just for simplicity. We try to be consistent about it in terms of being able to program a computer to do this for us automatically. So let me start by doing something that's called the left endpoint method. So for each subinterval, I'm going to take the left endpoint. So like here's the first subinterval. I'll take the left endpoint and plug it into the function. This is the function I never named called f. So I plug it in and I get a y value, which is up here. Okay, so I'm going to take that y value, which is of course f of a in this case. Let's do a little bit of accounting here. This first point is a. I'm also going to give it another name. It's going to be called x sub 0. This is a handy thing to use, the initial approximation in Newton's method. Now it's going to be the first point in my interval, x sub 0, the first x value. The next one is going to be, guess what? X sub 1, then x sub 2, and so on. And the last one, b, also will have an alias. b is also known as x sub n. Now this actually works out, because if you have n subintervals, you will have n plus 1 points. Let's try that out. For example, if we had, let's make 3 subintervals. 3 subs, okay? So starting from here to here, if we make 3 subintervals, it'd be like that. And how many points would we have? We'd have x sub 0, x sub 1, x sub 2, and x sub 3. Notice there are 1, 2, 3, 4 points, and 1, 2, 3 subintervals. So there's always one more point than there are subintervals. And notice here, if we start counting with x sub 0 instead of start counting with x sub 1, this all works out beautifully, because there are n points from a to b, and there will be there are n plus 1 points. So starting the count at x sub 0, there are n plus 1 points, there are n plus 1 x values, and n subintervals. All right, so what I'm going to do is plug in each left endpoint. I started with x sub 0, plug that in, and so this point would have coordinates x sub 0, f of x sub 0. We've seen this before. The next point, before I get to the next point, what am I going to do with that y value? I'm going to take that y value, which is f of x sub 0, and multiply it by delta x. And delta x, of course, is this distance right here. Now when I multiply this y value by this delta x, it's like taking the area of that rectangle, because it's length times width. So that's exactly what I'm getting, is the area of that rectangle. Then I'm going to add to that what I get if I plug in x1 into the function, which is going to give me this y value, right? And then I'm going to multiply that by delta x. So I'm going to get a rectangle that looks like this. And you multiply those two numbers together, the y value and the delta x, and you get the area of that rectangle. Right? Do it again for the next point. F of x2 would be this y value. You go all the way up to the curve, and then you multiply it by delta x, which is that big, and you get the area of this rectangle. Now, notice that this area here definitely overestimates how much area is under the curve. And notice that these two rectangles, their areas underestimated the area, the actual area. Well, yeah, what we're doing here is we're developing an approximation for the area. Oh, and it gets better. What happens when you get into this part where you have negative y values? Well, it's the same thing. The next point would be f of x3, and in this case x3 is going to give us a negative y value. This guy is negative, and we multiply that by delta x, which is always positive, and that's going to give us an area of this rectangle, except that this area here is going to be interpreted as a negative number because this guy right here, this f of x sub 3, is a negative number. So you're multiplying a negative times a positive. This is going to be a negative influence on the sum. So this rectangle has you could say has a negative area. And the same thing happens with this one, because when you take the y value of this point at the left end point of the subinterval and multiply by the delta x, you're going to get an area of that rectangle. Then from here, oh, notice what happens here. Looks like the y value right here is 0. So eventually, I don't remember what, this is x4, this will be x5. At x5, when you get up there, f of x5, this number will be 0 multiplied by delta x. So you're going to get an area of a rectangle that's 0. That happens. The next one picks up positive area. The next one picks up positive area. The next one picks up positive area that slops over most of the time. Then this one is here. This one goes all the way up to there. And there we are at B. Okay? So all of these areas added together all of these products added together, the last one will be, let's just put dots in here, the last one will be f of x sub, let's see, this is x sub n, the last rectangle, the next to the last point is x sub n minus 1. So if x sub n minus 1 gets plugged into the function and multiplied by delta x. So this is what we call the left endpoint approximation, or a shorter way of saying this is the left sum, or sometimes called the left Riemann sum. Riemann is spelled R-I-E-M-A-N-N, named after a famous mathematician, the left Riemann sum. And it's called the left Riemann sum because we use left endpoints at each subinterval. So pick a random subinterval like this one, for example, and the way you calculate it is you go to the left endpoint of the subinterval, that would be this guy, go up to the curve, and that's your y value, multiply that by a delta x, and it gives you the area of a rectangle like that. That's the contribution of this subinterval. Each subinterval has a contribution just like that, and they all get added together, and the sum is called the left sum for this particular way of chopping up the interval. All right? Now, let's simplify, simplify it from my point of view, complicate things tremendously from your point of view if you've never seen stuff like this before. This gets awfully awkward. So one of the things in mathematics that we have is a way of making shorthand out of this. And the way to make shorthand out of this is we use a special symbol to stand for a complicated operation. And this symbol is the letter sigma, capital sigma. Many of you who belong to Greek organizations know that sigmas are in Greek letters that come up with in lots of fraternities and sororities. But this is the letter sigma, capital sigma in Greek. And it's kind of like the letter S. It makes the S sound in the Greek language. And it stands for our purposes, sum. So whenever you see this symbol, it stands for sum. By the way, this is used in all areas of mathematics and science, especially in statistics. You will see this a million times. But we use it in math all the time, so get used to it. This symbol allows us to abbreviate this big, long thing without having to write this ... So, to rewrite this sum, all I need to do is to write an expression like this. The f is constant, in other words, that's not changing. I've got parentheses, that's not changing. The delta x is in every one of these terms, so that's not changing. we're multiplying those together. And what's inside the parentheses is changing. It's x sub something. Here it's 0, here it's 1, here it's 2. It goes all the way up to the last one, which is n minus 1. So what we use is a different letter to stand for all of those subscripts. So I'll use the letter I. So x sub I. Now what can you say about I? We say that I starts at 0 in this case and goes all the way up to n minus 1. So in English we read this as the sum, or the summation, if you want to get fancy, the sum of, and then whatever it is that you're adding up. And these are products, f of x sub I times delta x. Now, these are products, and I'm adding them up. Well, guess what, folks? That is part of an integral. Remember this? An integral is a limit of a sum of products of things that look like this. You multiply stuff together where this might be something, who knows, and this is a delta x. You add them up, take that to the limit somehow, and that's an integral. Now we haven't taken a limit yet, but we're getting there, because what this is getting us is, if you remember the picture, this is actually getting us a sum of areas that in some sense approximate the area as a signed quantity, S-I-G-N, a signed quantity under this curve, or the trapped between this curve and the x-axis, where we consider this part to be positive and this part down here to be negative. So here's the thing. This is kind of obvious, but maybe not. Suppose that I chopped up my interval into, let's say, 4 pieces. So let's draw a new picture here. So I've got this function, and I've got here's the x-axis as before, and here's my a, and here's my b, and I want to approximate the area that's under this curve. So what if I chop the interval from a to b into 4 pieces? All right, and I want the left endpoint, again, the left endpoint approximation. So here's the picture. That's the first. Second subinterval, I go up to the curve and draw the rectangle this way. Third subinterval, I go to the curve, which takes me down, and go to the next point. And then the fourth subinterval, I go up to the curve. Whoa! It's not very straight. And then across to B and down. So I've got rectangles that are here, 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 and here. So what is the sum of all of those rectangles? Well, we calculated that. But how does that compare to the actual area under the curve? Well, it's probably pretty grossly off. So what if I did a better job? What if I didn't chop up the interval into 4 pieces, but what if I used 8 pieces instead? Okay, so each subinterval now is like this. So I've got 8 points. So here's what the picture will look like. I go down to the curve. The first rectangle is partly the same, but now, instead of getting this part, my y value is up here, and so I come across like this, straight and down. And so this is the rectangle that we're talking about now. The next subinterval takes me up here and across and down. I may be losing points here. Now I guess the next subinterval is here, so I go across the same as before, but I have to stop when I get to the end of the subinterval. So this one is out because the next point takes me up here and across. And then from here, I don't know what happened here. Did I divide that up? I guess I did. So the next subinterval goes to there, and the next subinterval goes here. You see what's happening is I'm getting things that are closer to the curve than it was before. And if I chop the interval up even more, I'm going to get rectangles that do a better job. See, each time I chop it up more, the rectangles come closer to the curve. And if I do this on a computer, and we will in the lab, you will see the areas, the sum of the, or graphically, you'll see the areas of these rectangles fill into the curve and not slop over very much at all. So how do we get the true area? Well, we just take this sum to the limit. We take the limit as n goes to infinity, where n is the number of points that I chop up the subinterval, the whole interval from a to b into. All right, I think we need a small break. So let's take a little break here and see something totally different. I realized a little while ago that I should have put Tchaikovsky's some music from the Nutcracker on here, the Dance of the Sugar Plum Fairy. Maybe next time. Okay, cute. This is a little Alice program, but that's not for us. All right, so just to review a little bit, we've been talking about an integral, although I haven't shown it to you yet, but it's a limit of sums of products that involve multiplying things together that have a delta x in them. And one of the things that we can do with this is figure out areas. So we add up sums of rectangles that are obtained from left endpoints by plugging in left endpoints into the function, multiplying those y values by delta x, adding all that stuff up, and that gives us a left endpoint approximation or a left sum. Let's do it again. This time we're going to do it with right endpoints and just check out what the difference would be. So we have our curve. This time let's make it just simpler. It stays above the x-axis. Our interval goes from A to B, and we chop it into a bunch of pieces, all of which are the same width. And trust me on this, it's not going to matter too much if they're not. But it's easier if they are, because then the calculations and the programming can be done. So each one of them is delta x, and we calculated delta x. If there are n subintervals, then the points are a equals x sub 0, the next one's x sub 1, the next one's x sub 2, and so on, and b will be x sub n. So there will be n subintervals and n plus 1 points. So this time we're going to build using right endpoints, and so what we're going to do is on each subinterval, instead of plugging in the left endpoint, we plug in the right endpoint. So here's the first subinterval. So the first subinterval has this guy as the right endpoint. You plug him in, which means you use this y value, and for the first subinterval, you build a rectangle with that height. And so this rectangle's area would be the area that you use in your sum. So you're going to take f of x1 multiplied by delta x. And then you do the same thing with the second subinterval. You're going to take the right endpoint, which is x2 now, plug it into the function, and multiply it by your delta x, which amounts to going up to the curve here. When you get to the curve, that's your height. So your rectangle that you're thinking about looks like this. And then the area would be that, which is f of x2, that height, times delta x. And you can see as you go across that the rectangles that you're going to get look like that. Each right endpoint gives you a height of a rectangle. For this subinterval, the right endpoint is here. You have to go up to the curve, and that gives you the height of a rectangle, which then gets multiplied by delta x to get the area. So each right endpoint gives you a height, and so on. And the last one is this guy, and then gives you that rectangle. All right? So I can write it this way, so that the last area is going to be f of the last point, x sub n, multiplied by delta x. Notice the difference between this sum and the left endpoint sum. It's almost the same thing. The left endpoint sum starts with the first y value at x sub 0 and ends with the last y value at x sub n minus 1. But everything else is multiplied by delta x. Everything's multiplied by delta x and then added up. Here we start with x sub 1 instead of x sub 0 and go all the way out to x sub n. And this is your sum. Let's write this in sigma notation, the summation notation. So this would be the sum of things that look like f of x sub I delta x. But this time I doesn't start at 0, it starts at 1 and goes all the way up to n. So that is this sum in this compact sigma-like language. Now, I've done this. This is an approximation using right endpoints. If I chop the interval up into more points, I will have a better approximation for the area under that curve. Now, there's no reason why I have to restrict myself to left endpoints or right endpoints. You might say, could I do the midpoint? And the answer is sure. Here's the same kind of function, same kind of situation, interval from A to B. And we chop the interval up into a bunch of pieces. And this time, for each subinterval, instead of plugging the left endpoint in or the right endpoint in, we plug the midpoint, which is the average of x sub 0 and x sub 1. So that would be x0 plus x1 over 2. That gets plugged in. So that gives you this y value. And the area of this rectangle is what you would be calculating and adding to the next one, which is going to be the average of x1 and x2 plugged into your function. So x1 plus x2 divided by 2, plug it into your function. That gives you this y value. And you go straight across with that, building a rectangle. Looks like about the same height as the other one. Just an accident. Multiplied by your delta x to get the area. And the next one, the midpoint of x2 and x3, would be this guy. Going up to the curve takes you to here, and the rectangle height would be like that. And so on. The last one would be f of the next to the last point is xn minus 1, averaged with x sub n. So you add the 2 and divide by 2, plug the result into the function, which takes you up to about there. That's your y value. This is the rectangle that you would get using that y value, and the area of that rectangle would be this guy times delta x. So, to put this into compact sigma notation, it's the sum of things that look like f of, now this is going to get complicated, so I'll hold off on it, f of something times delta x, and the i's, let's see what this is. I'm going to focus on the first x. The I runs from 0 to the last one here is n minus 1 again. Now do a little accounting here. How many numbers are there from 0 to n minus 1 inclusive? There are n of them, actually. Same as how many numbers are there from 1 to n inclusive. There are n of them. There are n areas that you're adding up because there's one per subinterval, and there are n subintervals. So I'm adding up things that look like the average of x sub I, and this is a little tricky, x sub I plus 1 divided by 2. Now this is bookkeeping. X sub I is originally 0 when I equals 0, and x sub I plus 1 will be x1. So this means x0 plus x1 over 2. That's the first term times delta x. Now imagine letting I equal to 1. Then this means x1 plus x2 over 2. That's the second guy times delta x. And so on. So this captures exactly that sum. And this would be what's called the midpoint approximation, or the midpoint Riemann sum. All right. Oh, there's so many ways to do this. Let me give you another way. Suppose that you decide that instead of using left endpoints, right endpoints, midpoints, you decide that you're going to take your interval from A to B and chop it into a finite number of pieces, n pieces. For each piece, you'll look at your function and you say, I want to be the big guy. I want to be the maximizer. So on this interval, I'm going to pick the biggest value that I've got, which looks like it's going to be right there on top of the mountain. That's the biggest value, and that's what I'm going to use as the height. For each subinterval, I will pick the biggest that it gets. That's the height. Now this might seem like a really stupid thing to do. For each subinterval, you pick the biggest value. So on this subinterval, this is as big as it gets. That's the area that I'm going to use. On this subinterval, I'm going to use this height because that's as big as it gets. So I'm going to get a rectangle that looks like this on this subinterval. And on this last subinterval, as big as it gets is over here on the left. Now, this is called an upper sum because on each subinterval I find the maximum of the function and plug that in to get the y value. Find the maximum on this next subinterval, that's this guy, plug it in. On the next subinterval, find the maximum, plug it in, that gives me a height. On the next subinterval, which goes up and down, find the maximum, which is in the middle, but that's no problem. We use that as the y value. In other words, this point would be plugged in, gives us a y value, and that y value gets multiplied by delta x. Now, you might say that's pretty stupid because the upper sum is always going to be overestimating the actual answer. At least up above here, it looks like sometimes we slop over, sometimes we're under, and maybe on the average we might come closer to the actual value. Well, that's true. However, one of the things that you can say for sure about the upper sum is that the upper sum definitely overestimates the actual answer. No surprise. But here's the thing. What if you now turn around and do the lower sum? The lower sum does the same thing, except let's change colors. Do it in red. So the lower sum looks at the same subinterval and says, I want to pick the smallest value of the function, which would be right here. And I'll use this rectangle. So on the second subinterval, the function goes like this, and this is as small as it gets. So I'll use that rectangle. On the next subinterval, this is as small as it gets. So that's the rectangle. On the next subinterval, it goes up and down, but this is as low as it gets right there. So now I've got a rectangle like this. And on the last subinterval, as low as it gets, looks like it happens right around here, because then it starts going up again. So here is the rectangle that I'm going to get. So I have lower sum computed by taking each of these heights and multiplying by delta x and adding them all up. And what's the big deal about the lower sum? Well, it's that the lower sum is guaranteed to have a value that's less than the actual value of the function. So the actual sum of the actual area under that curve is guaranteed to be between the upper sum and the lower sum. Furthermore, I can sharpen both of these guys up by just chopping the interval into more pieces. The more pieces I chop, the better the approximations get. So the lower sum actually increases and the upper sum decreases. The amount of slop goes down, and yet the actual value of the area under the curve is still going to be trapped between upper sum and lower sum, so I get a better and better approximation for the area under the curve. What's interesting is that these are two other ways to do it, where the heights of the rectangles, like here, for this problem right here, I'm actually plugging in a point that is neither endpoint. It's somewhere in the middle. And it's not even necessarily the midpoint. It's just some point that gives you the actual maximum value on that subinterval. But you know what? It turns out that you could actually plug in random points. You could take a function on the interval from a to b. Well, it's crooked, but I'm sorry. From a to b, and chop it into a finite number of pieces, n pieces. And on each piece, you just sort of close your eyes and pick a point, like there, for instance. Go up to the curve and draw your rectangle, and that's your first one. Then do the same thing here. Pick a random point like there, go up to the curve, and that's the rectangle that you'd use. Now, if you're going to do this, let's say you label these numbers again, x0, x1, x2, x3. Let's do it for this particular way of chopping up, x5 and x6. So there are 6 subintervals, 7 points, but the names of the numbers that I'm going to plug in are going to look really ugly, but it's a bookkeeping device. On the first subinterval, the number that gets plugged in right there is what I'm going to call x1 star. That doesn't mean x1. It means the element of the first subinterval that I'm going to plug into my function f. Remember f? Plug into my function f to give me the y value, the height of a rectangle. This guy right here is my x sub 2 star, which just means some random number between x1 and x2, a random value on the second subinterval, which is going to get plugged into the function and multiplied by delta x. So we get f of x2 star times delta x. Now, could x sub 2 bar be the right endpoint? Sure. x1 star could be the right endpoint. All of these guys, the stars, could be the right endpoints, and then you would just get the right endpoint approximation. Or they could be the left endpoint. Each time, pick on the left one. Not randomly now, but pick the left one every time, and when you multiply that left endpoint height by delta x and add them all up, you get the left endpoint approximation, or the left sum. Or you could use the midpoint every time. See, this notation is very, very general. It allows us to write for the nth subinterval, we pick a random or an arbitrary y value and multiply it by delta x, and this is going to give us an approximation for the area under the graph. And in sigma terms, it looks like this, the summation of things that look like f of x sub I star times delta x, where I starts at 1 here and goes all the way up to n. So I equals 1 is the first value, going up to n. There are n of these things, and there are n rectangles that get added up together. Okay? All right, one last thing and then we'll quit, and that is an application of this that you might not have anticipated in a sort of a real-world setting. What if you had the graph of a function which represents the graph of the velocity? So this is the time axis going this way, and f represents, f of t is the speed or the velocity, speed at time t. And we're interested in the following question. If you start here and you end here, and this function is the speed that you're traveling. So here, you're going slow, and then you speed up, and now you're going slower, and now you speed up, and you're going slower, and you speed up, and then here for a while it looks like you're tapering off and you're traveling the same speed, right? But let's suppose that this is a graph of your speed. Now in real life you might be traveling 0 for a while and then build it back up and then back to 0, but let's say that this is the graph of how fast you're traveling. Question you might ask is, how far have you traveled in going from A to B? What is the distance that you've traveled? Well, you have a formula that you learned from elementary school. Distance equals rate, or speed, times time. And see, if your velocity, if your rate had been constant instead of going up and down and up and down, if your rate had been a constant, then all you'd have to do is multiply that rate, say 30 miles an hour, times the amount of time that it took. So your height would be the rate, and then the distance here would be the t value, how long it took you, and that would give you the distance that you traveled. Or what if you just chopped up this interval into a bunch of pieces, and for simplicity all of them are the same length, and on each piece you just take some random value, like that one, let's say, and you say that that's the best representative of the speed on that interval, and multiply that speed by the time. If you multiply the rate of speed, right? Speed means rate, times time, you're going to get distance, which means this is the distance that you've traveled over this first subinterval. Well, not exactly, but not too far off. You're slopped under and over a little bit. But then if you do the same thing on the next subinterval, just plug in some random number and use that as your y value, or left endpoint, right endpoint, doesn't matter. What you're getting is an approximation for the total distance that you're traveling. So this sum, this Riemann sum, is an approximation for the distance that you've traveled if you're given a graph of speed or velocity. So this is what we're going to be playing with in the next few days. I haven't shown you how to do any of the problems yet. So in class on Friday, you'll see some problems and we'll work on them one at a time. And they're actually quite simple. Don't panic. You just have to realize that all you're doing is looking at a particular function on an interval that they give you, chopping it into pieces the way they tell you, and using y values the way they tell you to use them, calculating areas, adding them up, and that gives you an approximation for something called an integral, or an area, or a distance, or many, 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 many other things. I can't begin to tell you how incredibly applicable the notion of an integral is. So you'll have to wait until Calculus 2 to see some of the many applications of integrals, and you'll go through quite a few. But you will see at that point that it's hopeless to try to do those problems by just thinking, I'm going to calculate some antiderivative or something or other. No, you can't do it. The integral is a limit of sums of products of things that look like this. They're y values of some kind multiplied by a delta x. Add them up and take them to the limit. And sometimes they're areas, sometimes they're distances, sometimes they're other things entirely, like work, for example. How much work is involved in pumping out a tank full of fluid. All of that kind of stuff is interpreted as an integral. Okay, so on Friday we'll do some simple problems in class that have to do with calculating what are called Riemann sums. Alrighty, see you later.